Hello again, everybody. This is the fourth workshop of 7 in our supervised machine learning series, where we are diving deep into Python and Scikit-learn. It's good to see people on the call again today, both on Zoom and on YouTube. My name is Alex Chisholm. I'm the co-founder of DataQuery. If you go to our site, you'll find a bunch of links, more than 2,400 right now, that'll take you to data science courses and online textbooks, tutorials, really anything that can help you build specific data skills and then ultimately compete for that data science job. As always, I'm joined by David Sponser. He's put together a really neat case study tonight that's both practical and interesting. What's new with you, David?
Not much, just getting through the Hurricane Ian that passed by last night, which was very exciting, but the damage wasn't too bad, luckily, over here in North Carolina. And I'm ready to get into classification. So we're shifting today from regression to the classification world, and it's going to be pretty exciting. We'll be working with I think, a very interesting data set, very practical, like you mentioned. So it's going to be a good session, I hope, for people.
Good. And if you're on the call, if you're joining us for the first time, welcome. I'm going to drop a few links in the chat box that you should be able to see. I'll do it both on YouTube and Zoom. But you'll be able to see just a link that'll take you to an overview of this workshop series. As I mentioned, we're doing 7 of these, and now we're moving into classification. You'll be able to find data and the code and links to the videos up on YouTube as well. And you can also go ahead and sign up for the next one. We're doing these every Saturday at 2 p.m. Eastern time in the United States. And again, we're really just glad that you're able to join. As David mentioned, the first 3 sections were all about linear regression. So we were trying to find a way to take our data, manipulate it if we have to, and then to make a numeric prediction. So we wanted a number coming out of it. Now we're going to turn to classification. We're going to again look at these underlying patterns within the data to try to predict, when we're looking at new data, what group or what class is something most likely to belong to. And yeah, there's a practical business case that David is putting around this. A lot of you that have worked with marketing teams or in the business analytics side, at least, will probably recognize a lot of the themes and the concepts that are there. Mm-hmm. If you are on Zoom, feel free to use the Q&A functionality. I'll keep an eye on that the entire time, and we'll interrupt David if anything comes in that is pressing. If you are on YouTube, just go ahead and use the chat up there. And I think with that, I know there's a lot of material tonight, and I think everything has been said that needs to be. So why don't we just hand things over to you, David, and let you start working on your material.
Thanks. All right, let me share my notebook here that we have in Deep Note we've put together for everyone. So hopefully everyone can open this up with the link we've shared. And I think it's best if you run the code, with us, just along with us, just to see how everything works, how everything comes together. And that will be the best experience for everyone. So as we get started today, so typically what I like to do anytime I'm putting together a notebook for any data science project is I like to import my modules and set up my notebook environment as the very first notebook cell. So that way, anybody that's running this notebook after you, maybe to run the model as well, can just clearly see what packages are being used for which aspects of the machine learning process are you bringing in these functions for, so it's all very clear. So the new ones today that are going to be different from the last 3 webinars that we did is our modeling component from Scikit-learn. We're going to be using logistic regression today to do classification. And then we also have some model evaluation metrics that are new from Scikit-learn today. So we'll be talking about those towards the end of this tutorial today. All right, so we're going to execute this first cell here just to load all of the things that we're going to need to fit our model today. So just a reminder that every single analytics project or data science projects that you will work on usually follows this data science process, these key steps that follow every single project. So we typically start off with our business understanding. So this is I think the most important part of any machine learning project. This is where we sit down with the business owners and the stakeholders and really figure out what data we have available, what we're trying to do, and what success means for this company. So without that, it's very difficult to fit a model, because then you don't really know if the model is good enough at any point, if you don't have that success criteria built in beforehand. And then we move on to the process where we understand our data. We have to prepare our data. So this is all the work we did with feature engineering. Last time we met, we were building feature engineering pipelines. And then we get on to the modeling, where we fit our models. And finally, we evaluate our models on our test data. So we've worked on these components before when we did our linear regression modeling. So in those examples, we were predicting the quality of wine, which was a continuous number. And we went through these process. We learned how to do feature engineering and modeling. So today we're going to pivot a little bit from the wine industry into marketing analytics. So we have a new data set we're going to be working with and a new business problem that we need to solve here. So here in this example, we're going to just assume that we've been hired as a data scientist for a large corporation, and they're seeking to optimize their marketing strategy. So what they're really trying to accomplish here is to automate their marketing outreach and their social media campaigns. Right now, what is happening is that their marketing managers are using historic data on customers coming to their website, and they're tracking things like the total number of clicks and the time they spend on the website and all sorts of other attributes, and where they're located, so their IP. And then we have the outcome, which is whether they purchased a product or they didn't. So here we have categories or groups that we need to predict. So here we have a yes and a no in this case. Person purchased or did not. So what has been happening in this marketing department is that they have been using just aggregate statistics from this data to update their marketing campaigns. So as an example, if a customer has visited their website more than 2 times, maybe in the past week, that's when they will go ahead and start emailing them discounts and all sorts of other things. But the success of these has not been that great. Their conversion rates are very low. And this is because they're not using all of the wealth of information they have on all these customer behaviors to make these predictions. And again, it's very manual. So people have to look at this data and decide who to mail. So it doesn't scale very well, right? What if you have millions of customers all of a sudden showing up, right? It's very difficult to manage that. And so this is a common problem, actually, that happens at a lot of companies and marketing departments. They're looking to automate how and when they should email, who should they send to, without having to think about it too much, because that requires too much effort, too much labor on their part. So after speaking with the business leaders at this company, we've determined that our success criteria here is whatever model we fit, we need to correctly identify customers who will make a product purchase at least 70% of the time. So among that group, so the people who end up purchasing a product, our model has to correctly identify 70% of those people on average. Because if we don't do that, then our marketing becomes more expensive than the effort. So then it doesn't make financial sense anymore for this company, right? So that is our success metric. And I will show you towards the end of this notebook how we can evaluate our model to see if we've met that on our test data. So the first thing that we want to do after we have done the business understanding is now we get to the data understanding. So what do we have to work with here? So let's have a look. We're going to load. It's the data file is called marketing leads CSV file. And here I'm calling it leads DF. I'm reading it in with pandas. And this is what we have to work with. So our target column here, so the thing we are trying to predict, is product purchase. And now instead of numbers, where we had in regression just continuous numbers, now we have categories, yes and no. And we have attributes of these customers. So every single row here represents a customer that took an action or did not. And we have the total number of times that they visited during a fixed period of time. We have the total time that they spent on our website, the pages that they have visited on average per visit, their total clicks. And then we also have their source. So this is the lead source. So this is how do they get to our website? So this could be through direct traffic where they just found our website. This could be organic search where they searched for us on Google and made their way to us, or through an email campaign. So all the various sources of ways that they can get to our site, and also their US region based on their IP address of their computer. So a really rich data set. And what we're trying to do today is make a prediction whether a new customer will make a purchase, yes or no, based on their features. So all of their behavior on our website.
And David, you have a pretty high proportion of successes here, right? You've got 36% of people that are actually buying a product. If that was, 2% or 1%, would what you're doing today still be applicable in the same way, or are there other considerations that you'd have to make?
Yes, so there would be other considerations, but what we are doing would be applicable. So we would be taking the same steps. There would just be one extra step we would need to take to pre-process our data. So that's known as class imbalance in classification, where you have a very uneven distribution of your outcome categories. So what you need to do is it's a technique known as bootstrap resampling, where you create data sets from the original data set that have an equal distribution of these yeses and nos. So that would be the first thing that you need to do. But then after that, once you have those data sets, all the other steps remain the same.
Okay, interesting. Thanks.
And there is a helper package to Scikit-learn that it's called imbalanced learn, and it's made for exactly that use case. It creates all those even balanced data sets, so you make sure not to make that mistake. But yes, but for us, not much of a concern. But we do have some concerns that I can already see. The reason I chose this data set is that we have a lot of pre-processing that we need to do. There's a lot of feature engineering that we need to take to make sure our model does well. And so let's have a look. We're going to do an exploratory data analysis just to understand our data here and identify potential issues. So first, let's start with our numeric variables. The first thing I like to do is use the hist method from pandas to make histograms of all my numeric variables. So this is a very handy method. You simply take your data frame, call the hist method, and here we have some optional parameters. So I have my figure size, a number of bins, and things like that. But again, these are just optional. But the nice thing about this hist method is it will make a histogram of every single one of your numeric columns in your data frame. And so the thing that sticks out here, there's two things we have to worry about. We have a fair amount of skewness across all of our numeric variables here, all of our features. So that is, again, it's not a problem for all model types, but for many of them, it is. It can lead to poor model performance when you have a lot of values just being, put into a very narrow range on your particular numeric column. And then you have a long tail of values coming out. So that is a potential problem for us. And then we also have a wide range in terms of range, of the numeric values. We see that the total web time ranges from 0 all the way up to 2000 seconds in total. And then we have things like web visits. The vast majority is between 0 and 5, I believe. So we have pretty vast differences in scale. So what we have to do for our feature engineering here is adjust for the skewness to make things more balanced, and then also normalize our data with something known as a z-score. If you've ever done that before, you'll be using the standard scaler from Scikit-learn to process this data and get it ready. And then we also have lead source and US region IP. So we have to convert those into numeric output to be able to go ahead and fit models with Scikit-learn. So what we'll have to do is create dummy variable encodings of these two columns before we can actually train our model, right? So those are the things I see here. Another thing you should always look for is correlations among your features. So to do that, here I'm using the same code that we used in our first webinar, where we made a heat map of the correlation matrix from our data. So here in this heat map function, I am passing a correlation matrix that I use with the core method on my data frame. So it calculates every single pairwise correlation between my numeric columns here. And again, these are just optional parameters, things like CMAP, but those are just the ones I like. It makes it very easy to see what's going on. And again, we have a couple concerns here already, and that is generally what I look for is if I have a correlation that's greater than 0.7 among my features, that's something that you should really look at and potentially remove one of those features from every pair that exceeds that threshold. So we have a very large one between pages per visit and total clicks. So that is 0.96. So that is almost a perfect linear relationship between those two. And it makes sense. I mean, the number of pages you visit and the clicks, you'll have more clicks to the more pages you go. So that's something we will have to work out. And if you remember from our feature engineering webinar, there is a transformer just for this particular problem. It's known as a drop correlated features, and that's going to handle this automatically for us. And I also like to make a pairwise scatter plot just to have a look at the numeric relationships. Now, again, if you had thousands of columns in your data frame, you probably would not want to do this because that would overwhelm your output. But in this case, where we just have 4, it's very informative to see what's going on here. So the first thing that I would look at is on the diagonal of this plot here. So here we have something known as these kernel density estimates. And this is for our groups, whether they did make a product purchase or did not. So I have my yeses in blue and nos in orange. And you want to look for if there's a large difference between these two groups on that particular column. So the largest difference would be for the total web time. So my yes group and my no group have very different distribution of values on this. So what this is telling me is that this will be a strong predictor of my outcome, yes or no. Okay. And then you also want to look at these linear relationships. So you can see total clicks and pages per visit. It's nearly just a perfect straight line between these two. So that's going to be the problem. So we need to remove one of those columns before our modeling. So either the pages per visit or the total clicks, because here it's just providing redundant information. I can tell you if a person clicked 50 times, I could tell you exactly how many pages they visited based on this linear relationship. So there's no need to include this. It's just going to make the model performance a little bit worse and the model more difficult to fit. But again, we're going to try to automate this with our feature engineering. And then finally, I also like to look at summary statistics by my target outcome. So for us, that is product purchase. So here I'm taking my pandas data frame, leads DF. I am grouping by my product purchase column, and I'm calculating the mean of all of my numeric columns here. And this will be nice to look at just to see if there are any differences between the two groups. And you can see here that for my no and yes groups, the greatest difference by far is again on my total web time column there. So again, that indicates that that's most likely going to be the strongest predictor that I want to use for my classification model. All right. And then finally, let's have a look at our categorical variables. So for these, I am making bar plots, and we can make these with the count plot method from Seaborn. So we just have to pass our leads df, our pandas data frame. We pass what we would like on our x-axis. So this should always be a categorical column. And then hue stands for how do I want these bars to be colored, by what category. So here I want them to be different by the yes and no outcome, just so I can see what the difference in counts are for my target column here. And when I look at this, what you want to see in terms of prediction power is a big difference in the counts of your yeses and nos for any particular category. So we can see that our strongest predictor for the lead source would be organic search here, because there is a vastly different distribution, right, for my yes and no group within that particular value for my organic search. So that is most likely going to be another very powerful predictor of our outcome. And then we can do the same for our region. So does product purchase differ by the region of our customers? And we see some actually really great differences here. So in the West and the Southeast, we have significant differences between my yes and no groups, and also in the Southwest. So it seems like location, where our customers are joining us from, matters a lot here. So this will also be very powerful predictor. All right, so now that we have explored our data, we have an idea of what's going to matter for our classification model. So during this step, you would, in a real data science project, you would want to go back to the business stakeholders and just have a discussion, right? So all the things that you have discovered, all the things that are driving these differences between these groups, you would want to talk about and make sure that it makes sense to them, since they work with this data on a daily basis and they know the business processes. You would want to go back and forth and just confirm your findings, just to make sure that your data is accurate. And then once that is complete, right, we have our success criteria, we understand our data pretty well. Now we know what we need to do for feature engineering based on all of our explorations that we did. And just as a reminder, this data preparation step, also known as feature engineering, is the process from taking our raw data set and converting it into a numeric matrix, because the vast majority of all of our scikit-learn models, they expect a numeric data matrix to fit all of their machine learning algorithms. So here's a nice visual of that, where we start with our raw data. And again, the technologies you use for this processing can vary depending on where you work, but typically you'll be using Python, SQL. If you have very large data sets, you might have to write Apache Spark code, or maybe R, just to convert everything down into the numeric matrix output here. But before we do that, what we should always do, we need to always remember this step. So before we start doing feature engineering, we need to split our data into a training and a test set. So that's going to be very important for us, because we will train all of our feature engineering steps and our transformations only on that training data set. We will fit our model to that training data set, and then we're going to make predictions on our test data set. And so this is critical, because you want to leave out that test data set to verify how well your model will generalize to new data. That's what we're going to be using to make sure that our model meets that success criteria ultimately. And you're also using that test data set to test out your feature engineering steps. So you want to make sure that your feature engineering pipeline is not going to generate any errors once you give it new data. So it makes you transform everything correctly and everything works without any surprises. So the way we do that in Scikit-learn is with the train test split function. And this will return 4 things to us. We have our train tests for our X, which is our features, and then Y, which is our outcome column. So the only things that we need to pass to make this work is we have to pass our data frame of features only. That's the very first argument. So here I'm saying leads DF, and I'm dropping the column product purchase because that's my target column. And then for the second argument, I'm passing my product purchase. So that's where I need my target column there. And here we specify how much we would like into our training. So here the 0.75 represents 75%. So it's going to randomly split our data. 75% will go into our training data and the remaining will go into test. And just make sure never to forget the random state option here. This is to ensure that if you run it again tomorrow, you get the exact same data split and you'll get the exact same evaluation metrics. So you want to make sure it's a reproducible process. All right, so we will go ahead and create all of our training and test data sets here. And let's just have a look at what we get back. So here I'm using the shape attribute of my training data to display how many rows and columns I have. And then let's have a look at the actual data frame that we get back. Now, as of Scikit-learn version 1.0, it's become much more friendly with pandas. So before you had to convert everything into a NumPy array to make things work. But now a lot of the Scikit-learn functions work directly with pandas. So this is why when we pass in a pandas data frame for my features, and then here I'm passing in a pandas series for my outcome, it's going to keep the same data type and data class when we get back from our train test split here. So our X train is a pandas data frame. It's got all the original data, except we randomly chose 996 rows out of the nearly 1,400 total that we have here. And then for my Y train, this is my outcome with my labels. This is going to be a pandas series where I have my no's and yeses. So the data type of this is an object. So it's a character series. But since we're doing classification, this is okay. We can go ahead and pass a series of categories to our modeling functions, and they will know that we're doing classification and everything should work just fine. So now on to our feature engineering pipeline. So this will be a review from what we did in the previous two webinars. But now we're going to apply it to our new data source here. So as a first step, I always recommend identifying your numeric features and also your categorical features. You want to make a list of both of these column names just so you could easily put together your pipelines. So that's what I'm creating here. My numeric features, I'm taking all of the numeric data. I'm using select D types for my X train data. I'm extracting the column names, I'm turning them into lists. And I'm doing the same thing for my categorical features. So I should get back two lists here, one for my numeric features and one that has the names for my categorical features. All right, and we have things working correctly here. So now I need to create two pipelines. So the first one is, what do I want to do to my numeric columns? And then the second one will be, what do I need to do for my categorical columns? So for the first one, for our numeric transformations, we want to take 3 steps. So these 3 steps I mentioned before while looking at our data. So we want to use Yeo-Johnson transformer to remove skewness. Then we want to use the standard scalar from Scikit-learn to normalize our data. And then finally, we want to drop our correlated features. So hopefully we can automatically remove pages per visit that is highly correlated with total clicks. So this is how we define this pipeline that will transform our data. So if I give this pipeline a data frame that has these numeric columns, it's going to make all of these transformations for me. So
hey, David, for the drop correlated features, is that just looking between 2 variables, or is it including, or is it looking at all of them when it makes the decision? And I'm curious because do you have any control over which of the correlated features you drop if there's one that might make more sense from a business perspective to keep in your prediction model when it goes into production.
Yeah. So I looked at that at the source code. So this is from Feature Engine, and it doesn't give you the option of choosing which one. It kind of automatically does that. So if that was a concern, then we would not use drop correlated features. We would have to write our own custom drop correlated feature, basically transformer.
Okay.
So it just drops the one that it's almost just randomly. You'll get the same drop every single time after it's trained, but you don't know what you're going to get the very first time. And the way we build these pipelines is we use the pipeline class. So this is from Scikit-learn. And what this takes is a list of tuples. And each tuple will contain what we want to call this step. So this is just a nickname that we're using for our pipeline. So I'm calling this Yeo Johnson. And then the transformer that you want to apply. So here I'm using Yeo Johnson transformer. So this is from our feature engine package. And then for my second step, I add another tuple where I have my standard scalar. And here my transformer is going to be standard scalar from Scikit-learn. But since it's from Scikit-learn, I have to wrap it in the sklearn transformer wrapper from feature engine, just to make sure that everything works nicely together. And then finally, my last step, I'm labeling this as remove core. And this is where I'm using my drop correlated features transformer. And I'm setting my threshold to 0.75. I think that's a good default if you want to automate the process, just to make sure to remove the very highly correlated numeric features. So we haven't done anything really up until this step. So these are just instructions. When you make a pipeline, you are just instructing the pipeline. I want you to do this first, then this, and then this. But nothing has been trained and nothing has been transformed at this point. So these are just a series of instructions. And we can do the same thing for our categorical transformation. So I'm making a pipeline, but now I want to create dummy variables. So I'm using the one-hot encoder from Feature Engine, and I'm specifying to drop the last argument, or sorry, the last value. So I get dummy variables instead of doing one-hot encoding. Okay, so here I have my categorical transformations. And then the final step is you have to combine these two transformations, right? So I want to process my numeric columns, then I want to move on to my categorical. How can I just put it together into a single feature engineering pipeline? So for that, we need our column transformer. So the difference between a column transformer and a pipeline is that a column transformer can be applied to certain columns of your data set. So it allows you to stitch together, do this for my numerics, do this for my categoricals, and maybe do this for my date columns and so forth. It allows you to create this pipeline of sequence of steps by columns. So it's built in a similar way. It also takes a list of tuples, but now we have 3 attributes in our tuple now. So we have what we want to call this. So here, this is numeric features. I'm passing my numeric transformation pipeline. Those are all the steps I want to be carried out. And I pass it to which columns should this be applied to. So this is my numeric features. And then I do the same for my categorical features, right? So we're going to do one after the other with our column transformer. But again, we haven't done anything yet. I always like to remind people that we've only created instructions here in this object. So I'm calling this leads feature engineering. To actually use this, we have to train it on a data set to be able to make all of these transformations. So all you have to do is go ahead and take your object, the leads feature engineering, and use the fit method. You have to pass your training features into this. So here I'm passing our pandas data frame, xtrain, and now it has been trained. So it will do a nice printout. It will tell you exactly what it's doing and what columns it is applying it to. and now it can be used. So once it's trained with the fit method, I can call the transform method on it, and now I'm testing it out on a new data source. I'm saying, okay, all the things you learned on the training data, go ahead and transform my test data with it, and let's see what we get. And unfortunately, the pipeline and column transformer is still kind of stuck in the NumPy world for the time being. So if you pass it a data frame, it will always bring you back a NumPy array of the transformed results. But it does work. So we see that the first row of our data, we see these decimal numbers. And remember, we had 4 numeric columns before, now we have 3. So there's likely the dropped correlated features got rid of one of those columns. And then I see a sequence of zeros and ones. So those are my dummy variables that were created. But what we really want to do is, for now, we want to turn this back into a data frame, just so we could have the transformed data and we can see and verify everything worked correctly. So to do this, you have to take an extra step. You have to create a data frame from this NumPy array that we get back with this transform method. So to do this, I'm creating this xtrain transformed pandas data frame, and I'm simply using the data frame method from the pandas package here. I'm passing the data as the NumPy array using this transform method on my trained data. So this is the same thing that we just got above. And I'm saying the columns should be from this method, get feature names out. So once you train a feature engineering pipeline, you could use that method, get feature names out, to tell you what the columns are labeled in the final result if you need it. So those are the only 2 things we need, and we will go ahead and build our xtrain transform. And so here, and again, I always do this step just to make sure my transformations are working correctly. And so we can see that our total web visits, total web time, pages per visit. So we dropped total clicks because it was highly correlated. And what about skewness? So before we had high skewness for all of our numeric columns, now much more balanced, especially total web time. It seems to be much more evenly distributed. And we can see that all of our numeric variables range from about -3 to 3. So they've also been standardized. So that's exactly what we wanted to happen. And then same thing for all of our categorical features. So we have lead source email, lead source affiliate. So now they are all 0, 1 indicators for the occurrence of that category in the original data. So this is what we mean by feature engineering, right? We have to take our data, we process it, clean it, and turn it into numeric output. And now we're ready for the modeling step. And we do the same for our test data. So I simply just go ahead and use my feature engineering pipeline, apply it to my test data, and then also use the column labels. And now we are ready to go. And the one thing I always like to mention here is just we have to remember that our feature engineering pipeline here was trained on our training data. And then we applied those transformations we learned to our test data. So that's a very important thing to do. So for our normalization, where we learn the mean and standard deviation of each column in our training data, we learn that only from our training data. And we use those same numbers to transform our test data. So that prevents something known as data leakage in feature engineering if you follow this process. So just always make sure to remember to use only your training data for your feature engineering. And so now we can finally get to the modeling. And whenever I teach at George Mason, I always mention this, that most classes you take in graduate school that focus on machine learning, they start off with a nice, beautiful data set that has no issues. And then you just focus on the modeling part and how to tweak models and evaluate them and things like that. But you're going to see very quickly here that fitting the model, it's literally just 3 lines of code with Scikit-learn. So most of the challenging parts of machine learning, all the mathematics behind the scenes, it's been abstracted away with Scikit-learn. It's actually very easy to do. And the most challenging part is really just the business understanding, the data understanding, and the feature engineering. I find that most people have trouble with that once they make it out into the real world and have to wrangle very messy data sets with lots of issues. So that's the part, if you've ever heard of that famous quote, I think McKinsey did a study on that, where data professionals spend 80% of their time wrangling data and getting things ready for machine learning. That's very accurate, even to this day. I've never spent less than 80% on any project for just getting data ready for modeling. But this is the fun part. Now we get to actually use machine learning to see if we can solve our problem here. So as we mentioned, Alex and I today, we're doing classification. So this is a little bit different than the regression scenario. So if we look at our sample data here, I plotted from our leads data set. So we see on the x-axis, I have total web visits, so how many times these customer came to our website, and then I have total time on our website on the y. And then I have, for every single point, which represents a customer, I've added color based on whether they actually made a purchase of that product, yes or no. So here we see that we have 2 distinct groups, right? We have our yeses, and then we have our nos in this case. And what we're trying to do in classification is to find a way to separate these 2 groups in our predictor space here, right? So is there any way we can maybe put a line or some sort of curve between these 2 groups to be able to separate them into these 2 distinct categories? And so the other terminology that you'll see in classification is something that's referred to as the positive class. So the positive class is simply the category in your outcome that you are trying to predict. So for us, that would be yes, right? So somebody does make a product purchase. And so that's the positive class. And then the negative class would represent the other outcome, which is no in our data. And these will be important for evaluating our model accuracy, which I'll show you in a little bit. So this terminology, so positive class, negative class. And so what we're ultimately doing here in classification is we're finding an optimal decision boundary. So it's known as a decision boundary. So this is usually a continuous function that's going to slice our feature combination space here into 2 distinct groups. And so with logistic regression, this particular type of model, it forms a linear decision boundary in classification. So if we fit a logistic regression model, we might expect to see something like that's displayed below here in this plot. The dashed line here represents our decision boundary. And then we have 2 regions. So above that line, we predict yes. And then below that line, we predict no, right? So that's what we're trying to do, finding the best function to split our data into these 2 groups. So the steps are very similar. If you want to fit a classification model versus a regression model, you simply just have to instantiate your model object as your first step. So here I'm using the Logistic Regression class from Scikit-learn, and I'm instantiating it, okay? And I'm calling this leads log reg. So this will build, my model object that I'm going to use. And to train my model, we just use the fit method once we've defined our model. So I take my leads log reg, I use the fit method, and I pass it my xtrain transformed. So this is where we have applied our feature engineering steps and gotten our data ready. And then I also pass it my labels, which is ytrain. So this is my series of yeses and nos. And it's going to go ahead and train my logistic regression model. and learn that optimal decision boundary to split these yeses and nos in my Y-train outcome. Now, unlike regression, we have two different types of model output in classification. So in regression, we only had one type, where when we called the predict method on a linear regression object, we always got back numbers, right? We got the predicted values for whatever we're trying to predict. But in classification, we need two different types of things. So the first one is we need the estimated probabilities for both my yes and no outcomes. And this we can use the predict underscore prob function from Scikit-learn. And then we also need a column that has the predicted outcome values. So this would return an array of yeses and nos. And so that's what by default, what predict will give back to us, just my array of yeses and nos. So I think it's helpful just to see what this output looks like. So here we have leads log reg. So that's my trained model that I just fit. And I'm calling predict on the X train transformed. So I want the predictions for the first 5 rows here to be displayed. So we get back a NumPy array. And here you see no, yes, no, no, yes. So here we get back the categories. And then we can use the predict proba function for the same rows. But this is going to give me back an array that has 2 columns. And all of these numbers are estimated probabilities. So this is you can think of it as the confidence of the model and thinking that this row is actually this particular outcome. But we're still missing one thing. We have these 2 columns. We get this NumPy array, but I don't know what they correspond to. Is the first column corresponding to no, or is it corresponding to yes? Right? Which category does that refer to? So to do that, we have to access this attribute of our logistic regression model, and it's the .classes underscore attribute. So that will give you the ordering of the labels that your model used. So here I see a no and a yes. So the first column represents my no, and the second column here represents my yes. All right, so that's what we need. So this is a little bit different from regression because, again, we get these estimated probabilities in addition to our predicted outcomes. And I did want to mention that there is a threshold. There's a default threshold of 0.5 that is used to create this outcome label array here, this no and yes array. And what that means is that if the estimated probability of a yes, so if we look at the second row of our output, we see that it's 0.69 for my estimated probability of a yes. If that's greater than or equal to my threshold value, which is 0.5, give me back a yes. Otherwise, give me back a no. So this is why for the second row, we have a yes prediction. So that's how this thresholding is done in classification. And the default cutoff value, the 0.5, that is what is used to draw this decision boundary here. That is exactly where that estimated probability of a yes is equal to 5 or 0.5. That's that decision boundary. And that's what you use to make your predictions ultimately. And so here, what I wanted to do is show you how to put all of this together on your test data set. So how do we get our original test data? How do we add our predicted outcomes, our estimated probability columns, and our original features? So this would be great to have because then we could explore where the model is making mistakes and maybe why is it making mistakes? Is it for particular values of our features and so forth? It's very important to analyze your errors in regression and in classification. And this is a little bit challenging to do because you have to build up a data frame of results, and it requires resetting your index for a lot of things. So if you don't do this right, it can be very, just kind of stressful for beginners. I just wanted to show you how this is done if you ever need it. So what I'm doing first is I'm creating my model outputs. So here I'm taking my predict output, which is going to give me my array of yeses and nos on my test data set. and I'm turning it into a pandas series, calling it product purchases, predict product purchases. And then I'm turning this array that we get back from predict proba into a data frame with the correct column names. So here I'm taking my predict proba on my test data, and I'm passing the column names using that dot classes attribute from my trained model. So now I have my model output. I have a series, and then I have my data frame of estimated probabilities. So then I have to use my PD concat function. So this pastes series and data frames together into one. And I'm doing it along axis 1, which stands for columns. So I'm simply taking my predicted product purchase, yes or no, and then adding on the estimated probabilities to it and creating a single data frame, right? So here I'm calling this model results. And then I'm using the insert method for that model results. And I'm saying in the very first position, the first column of this data frame, add something that I want you to call product purchase. And this is simply my Y test. So this is the actual outcomes for everybody. But if you don't do this part, that's where you will get a lot of errors, and people don't realize that. You have to reset the index on your Y test because the index doesn't match the things that you just created. And then pandas they're not going to match up and align correctly. So that's the important takeaway from this. You have to drop your index. And then I'm simply naming the columns what I would like. So here I'm just renaming them to something that's more readable. And then the very last thing, I'm using PD concat again, and I'm adding my X test. So those are my original feature values. And again, I have to reset my index to make sure everything works. So that was a lot. I was debating whether to add this or not because it can be confusing, but this is such a common use case that I think it's important for you to have this code to be able to build it if you ever need it in the future and save yourself just a little bit of the headaches that come along with things like having to reset your index in pandas. So let's see what we get. Just beautiful. Every time I see this, it's just beautiful. We have what actually happened, product purchase. So no and yes, right? We have what our model predicts using the default 0.5 threshold. And then we have our estimated probabilities, prob no, prob yes. So these two, in a row will always add up to 1. And then we have our original untransformed features. So now we can do all sorts of things. So we can look at what's the distribution of my predicted probability for my yes, for people that are organic search from the Southwest, or for people that do different amounts of total clicks. What's the difference between all of these groups? You can do some really cool analysis here that you would most likely want to do if you're presenting these results, right, to the business stakeholders. So again, it's a good skill to know how to build it. And then the final section here is how do we evaluate a classification model? So this is the part that's very different from the regression setting. So the first thing we need to talk about is a confusion matrix. And when I first learned about this, it was very confusing. I mean, it's just funny that it's called a confusion matrix, but all these terms, true positives and false positives, just confused me for a long time before I finally got it. But the way you build this confusion matrix is on the rows, you have the actual outcome, and then on the columns, you have predicted. So to build one, you need 2 arrays, right? You need 2 NumPy arrays. So the one is with your actual yeses and nos, and the other one is from your model that predicted yeses and nos. Then you simply look at all the unique combinations that happened, and you count them, you tally them up. So a true positive, and here we see a plus sign and a negative. So this is where that terminology comes from. So for us, positive means yes, right? They purchased a product, and no is a negative. So a true positive, everything on our diagonal here, true positive and true negative. With true positives, we predicted they will purchase, and they did. And then same thing for negative. We predicted they will not purchase, and they did not. The off diagonal is where we get our errors. So a false positive So that means we predict this person will purchase and they actually do not, right? So it's false positive. And then false negative is we say this person will not purchase, but they actually did, right? So these are the two types of mistakes we can make in our classification model when we just have two outcomes. This is known as binary classification. So what we need to do is have a way to tally up all of these counts for us. And there is a function in Scikit-learn in the metrics submodule, and it's called confusion matrix, and it will tally up all of this stuff for us. And what we need to pass is known as y true. So this is what actually happened. So this would be our y test, and then y underscore PRED. And this would be our PRED product purchases. So this is that series that we made here in the second column of our test data frame. So this gives me, this is basically what we're passing to all of these metric functions. The first column from my data here, and then the second column, right? What happened? And then what did we predict will happen in terms of yeses and nos? And now the other kind of insider important thing to keep in mind is you should always order your labels so it should be positive first and then negative second. So your positive class is first. So here it's yes, and then we have no. Otherwise, it would order it alphabetically, and you would have a yes and a no in the output, and you would think that your false positives, but they're actually your false negatives because things are in reverse order. All right, so this will give us our counts. And again, it's not the best function in Scikit-learn because you don't get labels. You get this array of numbers. So this is why it's, again, very crucial to know what the order is, and you specify here labels. So on my rows, I have my yes and no, and on my columns, I have my yes and no. So now I can tell that I have 95 true positives, 172 true negatives, and then I have 38 false positives. Okay, and then 27 false negatives. So this is where I can get all of my counts in my confusion matrix. But that by itself is not the best, way to evaluate your model, really, because it's dependent on how many rows you have in your data, because you're dealing with these raw counts. So that can be difficult to interpret. So this is why we have other metrics that convert this into proportions. So this kind of standardizes this evaluation. So the first one is known as recall. And the kind of secret I use to remember what this means is I just remember recall starts with an R. So that represents our model's accuracy among the real positive outcomes. Okay, so the people that really took that action, that really purchased the product, how well did my model do just among that group, right? Just my positives. So in terms of my confusion matrix, I simply take my true positives and I divide it by the row sum, because that gives me my actual positive count. So that's my accuracy. So from our numbers, our confusion matrix, we simply take our 95 and we divide it by 95 plus 27. That's the total number of actual positives we had. And here we get 0.78. All right. Now, there is a function to calculate this for us in Scikit-learn. It's called recall score. And again, it takes the truth, our predictions, but you have to provide what is the positive label, or what's the positive class. So for us, it's yes. So when we do that, we're going to get the same thing. There's my 0.78 if I round, right? So that's my recall. Another important one is precision. And to remember this, just because I can't keep this straight in my mind, even to this day, is I just remember it starts with a P. So this is the accuracy among my predicted positive outcomes. Okay, so of the people that my model predicted as that they will purchase, how many did I get correct? What was my accuracy among that group? So this one is a special column sum where we take our true positives and we divide it by the column sum there. And so here we get a 0.71, so 71% accuracy, which is great. And we can calculate that with precision score. So this is from our Scikit-learn. And again, we just pass our positive label there as being yes. And there we will get our 0.71 that we could get manually with our confusion matrix. So these are very important. But the only downside I wanted to bring up about this recall and precision is that you have to track two numbers in your mind. And for every different threshold you try for your classification model, you're going to get a different precision recall pair. So that can be difficult to optimize. Generally, you want to have just a single number of model performance. And so this is why typically the F1 score is used. And all this does is it combines this precision and recall into a single number. And it gives each one equal weight. And it's with this special formula. You multiply precision and recall, you divide it by their sum, and you multiply that by 2. And that gives you something known as an F1 score, which ranges from 0, being the worst, to 1. But in practice, you usually don't want an F1 score less than 0.5, because that is not good at all, right? You typically want to shoot for somewhere around 0.7 or more is where your model starts being good. All right, so to calculate this for us, it's the same exact format. All we do is now we use F1 score, but we pass it the same parameters. And we see for us, we get a 0.75 if we round up. So that's pretty good. And so if we go back to our business objective, right? So success was we needed to capture at least 60% of the people that will actually convert. Or let me make sure that that's correct. Let me go all the way back up to the top. So we have it here. Oh, it's 70%. So we need to correctly identify at least 70% of the customers who will purchase, who will make a purchase on average for this to be successful. So we have done that because we could use, in that case, our recall. Right? So that's the metric that's important for us. So these are the people that actually purchased a product. And our model, our estimate here is 0.78. So if we use this model, if we put it into production, based on this estimate here, we could expect that about 78% of the time, it's going to correctly identify a person who actually will make a purchase in the future. Right? So that's more than our 70% that was required. So here, we know that our model is good enough to meet that standard. And the last thing I wanted to show you is the built-in classification report from Scikit-learn. So this will take the truth, which is Y test, our predictions. So this is our array of yeses and nos, and our labels. So this is the order that we want the output. Now you have to print this output out just to make it look nice. But what this gives us is our precision recall F1 for within every single category. So we've already calculated the yeses manually, right? So there is our 0.71 precision, 0.78 recall, and then 0.75 F1 score. So that is the default definition of these metrics. You're only concerned about your positive class. And support here means how many rows of your test data were actually that outcome. Yes, right? So we have 122 customers here. Now, the nice thing about this is you can also look within your no category. So we had 210 people that did not make a purchase. And here we can calculate precision as well, just within that group. So if you remember the P here, so precision is among predicted. So among the people that our model predicted will not purchase, how many did it get right? And here it's 86%. And then same thing for recall. So here is where our model, what's our accuracy among the ones that really, so R, that really did not purchase, and that is 82%. So the nice thing about this output is you can look at the performance in both of your categories, which you should always do. And then at the bottom, it averages these out. So the first one, the macro average, is just an average of all those metrics. And then the weighted average is weighted by your support. So that's how many customers actually fall into those categories. It's used as a weight to estimate it. So this gives you kind of an overall precision and recall, taking into account your performance within each group as well. So it's a nice feature from Scikit-learn.
Now, David, you're showing a lot of numbers here, a lot of choices you could start with when trying to communicate what was good. When you are working with a CMO, a chief marketing officer, or somebody, where do you start with just to give them the sense on, is this model performing well or not?
So that depends on that success criteria. So if they give you something specific where they're focused on, I really need, so among the people that really will take this action, I need this amount of accuracy. So then in my mind, I know, great. So that's my recall. But of course, I don't tell them, I don't use the term recall in my explanation. I just say, so within that group, this model on average is 78% effective for that. And that's greater than your 70% need. So this model, I think, is great for you. But then in other cases where it's unclear, sometimes you will get, well, right now we just kind of pick customers at random and it's working horribly. We just need something that works better than that. So in that case, if it's up to me, then I like to use the F1 score. And I just like to say that this ranges from 0 to 1. But again, you don't want anything less than 0.5. That would be a so-so model. And then I use that as my metric. So the closer I am to 1, the better and better. So 1 is perfection. That would be your model made no mistakes at all. So again, if you get a 0.8, 0.9, you could almost use it as a letter grade almost. You know, sometimes convert it to an A or a B plus in terms of model performance based on those F1 score ranges. And that typically makes sense.
Right. And these measures of accuracy are pretty consistent across the different classification models you could apply to this. One question that came in was, we've started here with logistic regression. Why? And what else should I be considering for a problem like this?
Yes. So logistic regression, I think, is a great place to always start because it gives you a baseline of the model performance you should expect. So with the linear regression, we make that linear decision boundary. And so it's a very simple function, but you could use other functions such as decision trees, which make rectangle boxes out of your feature space, which can capture more complex patterns. Or then you have things like support vector machines or neural networks, and those can create all sorts of decision boundaries, curved decision boundaries and things like that. So your model accuracy tends to increase to a certain point, but then, so typically you want to try not all of them, but just a range of them. You want to start with logistic, move to more complex models such as decision trees, random forests, maybe try a complex neural network, and then see how these metrics change on your test data set for each one. So you have to find a sweet spot between, is this model overfitting? Because you can get to that point if you fit maybe a neural network and you do really well on your training data, but then you do horribly on your test data. That means that your model is almost chasing errors in the data. So that's kind of the typical process. You usually don't pick one classification model and that's all you try. You typically try 6 of them, 10 of them sometimes, different configurations. And this is where the experimentation part comes in data science. But we're going to get into that in our series when we go into building machine learning pipelines. So what we're going to do there is we're going to build a feature engineering pipeline. And then as the last step, we're going to add a model type to it. So that's where you can try a logistic regression, a decision tree, a random forest. You simply make pipelines for each one, and then you train all of them at the same time. And then you see how you perform on these metrics. And ultimately, that's what you use to make your final model decision.
Perfect.
Yeah, there's a lot that goes into it. And there's some aspects where some people say it's kind of the art of data science. The art part is really the feature engineering. It's known as knowledge representation. I will probably prepare features differently than somebody else with different types of experiences. I mean, there's general kind of best practices around that stuff. But again, it depends on that particular business, your understanding of that business. That's what determines what features you engineer. And ultimately, that's the most important part to get better model performance is the features you're passing into the model. That's by far the most important thing. Yeah, so good questions. And I went over again. I always tend to do that. I just pack
No,
in so
it's
much
fantastic. I mean,
material.
at this point, you put together about 4.5 hours worth of content on these between the regressions we started out with on the linear side and now into logistic. This was the 4th workshop. As I mentioned earlier, the 5th one is going to start next month on November the 5th. It's hard to believe that it's almost the end of 2022 already, but here we are. We hope that people that joined today, either on Zoom or on YouTube, will sign up and join us for that November 5th outing. And if you want to go onto our YouTube channel, you'll be able to get all of the old videos, and they have links to the code, to the data, and to other resources from these sessions. Any last words, David?
I just look forward to continuing our journey here. So we've covered the basics of classification here and how to evaluate it. But things are going to start to get really powerful starting next time, where we start building all those pipelines and I show you how to test maybe even just 10 models all at the same time. That's really where the power of Scikit-learn really shines, and all these pipelines. It allows you to quickly iterate, and we're going to get a lot of cool stuff.
And I think what is becoming clear, it all just is experimentation, practice, experimentation, and then an understanding of business context. I think those three things together are very, very helpful. And if you're on the call and you want, other resources to learn this, of course, dataquery.com has all of those thousands of courses that I mentioned linked to on the Coursera's and the data camps and the free textbooks of the world. So check out the site, type in classification models, type in logistic regression, and you'll be able to find something to dive even deeper into this material as you're working toward your data science, your business analytics, or your data engineering roles that you might have in mind. So we wish you all a good October. We will see you on November 5th, and please reach out with any questions. Take care. Good night.
Bye,
Good
everyone.
day.